Hello, this is my submission for the Quantum Project Final. I want to also mention that the link for the GitHub repo is in the description of this video. Also, it's going to be in the PDF that was submitted. So, to explain what a quantum computer is, a quantum computer is a special type of computer that utilizes the principles of quantum mechanics to perform calculations that are beyond the capabilities of a normal classical computer. So quantum computers use something called quantum bits, or qubits for short. In a normal computer, we use bits, and those um, and instead of they use those qubits to represent and store information. This allows a quantum computer to perform certain types of calculations much faster and much more efficiently than a classical computer would be. So quantum computers work by taking advantage of the unique properties of quantum mechanics, which is a special types of physics that deals with the behavior of matter and energy at the atomic level and the subatomic level. In this quantum world, particles such as electrons and photons can exist in multiple states simultaneously, which what we call as a phenomenon known as superposition. So one atom can be one. If it's pointing up, it can be one, or if it's pointing down, it can be zero. And then it can be both 1 and 0 at the same time. And then depending on how we take a picture of that atom, or we take a screenshot of it to see what value it has, it will choose one position. And we can take more than one picture at the same time, so we can get like 4 results out of one qubit. And there's also another concept that's very important to quantum computers, which is called entanglement. And that means that the properties of one qubit becomes correlated to a different qubit, even if they are separated by large distances on the atomic level. So if one qubit changes position, it will affect the position of a different qubit that's not really close or connected to that qubit physically. These properties of quantum mechanics allow quantum computers to perform certain types of calculations much more efficiently than a classic computer. For example, classic computers use algorithms that involves trying out different combinations of inputs in order to find the correct solution to a problem. This can be a very time-consuming process, especially for complex problems. Quantum computers, on the other hand, use a process called quantum parallelism to perform many calculations at the same time. So with a classical computer, it can only perform one calculation at one time, while a quantum computer can do more than one calculation at the same time because of the superposition of the qubit, where it can screen it in different ways to get different bit values, so it can do different processes and different calculations. This allows the computer to solve certain types of problems much faster than a classical computer. One example of this is a quantum search algorithm, which allows a quantum computer to search through a large database much faster than a classical computer. Because, for example, a classical computer will search the database one by one, while the quantum computer will search it more than once at a time. So quantum computers are still in the early stages of development, and they face a large numbers of challenges. And one of the main challenges is that they are very prone to errors due to the delicate nature of the quantum state. For example, for us to be able to set a qubit to 1 or 0, we need to have it at a very, very low temperature of almost close to absolute zero, which is in some cases colder than outer space. So it's the smallest amount of disturbance can affect the results of the qubit and gives us a error in the readings that we get. So we need to this means that they require extremely precise control and measurement in order to be able to function properly and be actually useful to us. And the challenge is that computers are difficult to scale up, as the number of qubits need to perform certain calculation grows exponentially. For example, with a classical computer, we can have like hundreds and hundreds of bits, but with the IBM ones, we only have 5 qubits or 7 qubits that are free and open to the public. And for there is also ones that have like 32 bits or 64 bits or 128 bits, but then it's very hard to go beyond that because of the nature delicacy of the qubits and how hard it is to maintain, to maintain it in a safe place. Despite these challenges, quantum computers have the potential to revolutionize a wide range of industries, including finance, healthcare, and defense, and cybersecurity. They could be used to solve complex problems that are currently beyond the capabilities of classical computers, such as optimizing the supply chain logistics or developing new drugs to solve for diseases. In conclusion, a quantum computer is a type of computer that utilizes the principles of quantum mechanics to perform calculations that are beyond the capabilities of classical computers. They use quantum bits, or qubits for short, to represent and store information, and then they can perform certain types of calculations much faster and more efficiently than classical computers. While they are still in the early stages of development and face a huge number of challenges, quantum computers have the potential to revolutionize the industry. Now I'm gonna switch it so I can show my screen to explain the quantum program that I created.
Okay, this is my quantum program that I did for the final. It is a implementation of Shor's algorithm. Shor's algorithm is a quantum algorithm for efficiently factoring integers. It works by finding the period r of a function fx modulo n, where n is the integer we want to factorize. If r is even and fx equals a to the power of x mod n, where a is an integer coprime to n, then the prime factor of n are n divided by the GCD of a to the power of r divided by 2 minus 1 by n. The Qiskit program that I provided implements Shor's algorithm by first finding a random integer a such that the GCD of an equals 1, where n is the integer we want to factorize, It then applies the quantum part of Shor's algorithm using a quantum circuit with 2 qubits and 2 classical bits. The quantum circuit applies the Hadamard gate to the first qubit, which is controlled by the controlled rotation gates to the second qubit, and a controlled NOT gate between the 2 qubits. And then we add another Hadamard gate to the first gate. These gates are used to calculate the function fx equals a over x mod n and find its period r. Finally, this executes the quantum circuit. We place the results in x and y, and then use the measurement results to find r of the function y times a divided by x mod n, and calculates the prime factor of n. And then we store the factors into a variable called factors, and then we have a for loop that goes through that one and prints all of them out. So for this example, I used 15. So if I were to run it, well, I already ran it, but let me run it again for the sake of differentiation. And you can see it's going through the cells, and then we get the factors of 15 are 15, 1, 3, and 5. Let's say we want to find 8. That's 18. The reason I'm using small numbers is because it's easier to verify fast. You see it's 1, 8, 2, and 4, but we can also use a big number. Let's say like 1,574. I have no idea what the factors are for these numbers, but we're going to find out right now. So it tells us it's 1, 1,574, 2, and 784. Let's try a bigger number. Obviously, it takes a little bit longer to find those. And then for that number, apparently these are all the factors. One of them is 1 times itself, 2 times its half, 4 da, 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 da. This is not a prime number, so it has a lot of factors. And that would conclude the code for my implementation. This notebook is going to be on the GitHub, so you can view it and run it for yourself. Thank you very much. I forgot to actually run my program on a actual quantum computer. So in the previous section, I just stopped on this one where it showed us the factor of this very large number. So we had IBM Q, and then I then ran it on a quantum computer. So I had an IBM Q.load account to load my account, and then I set up the provider, and it shows this server, which is located in Belém. I executed the job, and then I got the job.result over here into the counts, and then Quiskit.tools, and then imported this so I can monitor the job, and then said job status, job has successfully run. I extracted the measurements again, and then I used the measurement results to find the period of the function. And after that, I found all the factors, added them to the list, and then went to the for loop again to create this, to append all of these. So to show it again, I'm going to pick a smaller number, which is slightly easier to run. Hopefully the load time won't be as long. So let's restart everything. And as we can see, it's running through all of them, 1, 2, 3, 4, 5, 6, 7, 8. Now it's at the ibm.load.qn. I loaded my account, did this. Now it's sending it to the job to be executed, which usually this takes a little bit of time. Hopefully it doesn't take too long. While we're waiting, let's see. Did it find this one? It did find it in this one. So I will probably cut the video and then come back when it's finished doing this one. Okay, it looks like it completed it. We got job status, job has successfully run, and then it went through it again, and then we got 1:15:35, which matches what we have over here. Thank you again. Have a good holiday season.